Hello everybody. Let us review transformations of functions. So you see here 4 different translations. Translations are shifts. For the 2 horizontal shifts, shifting left and shifting right, you see that we're transforming the x-coordinate before it's an input to the f function. So if you apply a transformation before you give to whatever it is that you're giving as an input to the function, that's going to have an effect on the x-coordinates. It's going to have a horizontal effect. Meanwhile, if you want to shift it vertically, here we're adding c or subtracting c on the outside of f of x. So what that's doing is it's transforming the y values, because the y values are the outputs from f of x. So it makes sense that if you would transform the y values, you would have something vertical happening, because that's what y values affect. And if you transform the x values before their inputs to the functions, then you would have something horizontal happening. The only, I think, counterintuitive thing, which I'm sure you remember from last year, is you might expect that adding c to x would cause a right shift, because when you think about increasing x values, when they increase, they go to the right. But actually, that transformation has the opposite effect. The reason why has to do with the fact that you're transforming the inputs before evaluating the function. But the real deep explanation about why has to wait for a longer video. This picture captures scaling and reflection. So if our parent graph is here in black, if you were going to take the opposite of the f function, that would take the opposite of the y values, and so it would reflect all the y values, and that corresponds to a reflection around the x-axis. If instead you were going to take the opposite of the x values, that would be a horizontal reflection across the y-axis. If you multiply on the outside by a value of c larger than 1, that's like taking each y value and multiplying it, and so that's going to scale it upwards. Meanwhile, if you divide by a value c that's larger than 1, that would be like taking every single y value and dividing it by c, and so that would end up scaling it down towards the x-axis. This set of examples compares and contrasts vertical scaling with horizontal scaling. So on the left-hand side, you see the cosine function in purple here, and you see what happens when you vertically scale it. So if you multiply by 2 on the outside, you see that all of the values become larger in magnitude because the y values are getting multiplied. So 1 becomes 2, 0 stays at 0 because if the output of cosine is 0, 0 multiplied by 2 is still 0. So you see that it scales away from the x-axis. If you multiply the output from the cosine function by 1/2, that's like taking each of the y values and dividing it in half. And so that's why this wave is half as tall as the original cosine wave. So if you multiply by x by a constant on the inside of the function, that's going to be a horizontal scaling. So you're going to either stretch or squish it horizontally. So again, in purple, you've got the untransformed cosine function. If you multiply by 2 on the inside, you might expect it to get larger. You might expect a horizontal expansion. But just like in the case up here, where horizontal transformations have the opposite effect of the one that you might expect. Down here, if you multiply by 2, that's actually squishing it horizontally. So it's like all of the x values kind of get divided by 2. And again, I know that that's counterintuitive, and if you weren't told last year why that should make sense, that's something we definitely need to do this year, but it's a longer topic than this video. So then to round it out, if we are dividing by 2 on the inside, you might expect that to be a squish, but in fact, it's going to be a stretch. It's going to be an expansion. So we're taking the purple curve and we're stretching it horizontally. This illustrates the kind of thing that you want to have happen in your head relatively quickly. So if you have a parent graph, root x, you should pretty quickly be able to imagine the effects of shifting it right by 2, or reflecting it vertically, or scaling it vertically. Because you're going to want to be able to take these pieces of your function and freely move them around to build functions that look the way that you want them to. So let's do 3 examples that I hope are simple in review for you. Let's imagine f of x is x squared, so that quadratic formula. I want to transform this pink curve so that it is upside down and its vertex is up here. So if you have memorized a bunch of stuff about vertex form forget all that stuff. You can just think about it using transformations. So if I ignore the actual equation and I just work with f, it seems like what I want to do is shift it right by 5, shift it up by 8, and then reflect it. Well, I wouldn't reflect it. I'd reflect it first, then shift it right, then shift it up. So if I start with f of x, that reflects it, so that would flip it upside down. Shifting it right by 5 would be x minus 5 on the inside, and then shifting it up by 8 would be plus 8. So that would be one way of writing down the set of transformations you need to apply. If we want to do it with the actual equation, same thing. We'd start with x squared, but instead of being x squared, it would be x minus 5 squared. We'd reflect it, and we shift it up. You should feel comfortable working in both systems, either working with equations or working just with the function names. What if I wanted to transform it so that its vertex is still at 0, 0, but it passes through the point negative 10, comma 1? Of course, you could write the quadratic equation with some coefficients, and you could try and solve for the coefficients. But again, in this case, I think we can just do it with transformations. What I want to do is I want to horizontally expand it. I want to horizontally stretch it this direction. So in the language of functions, instead of x, we would have x divided by 10, because that corresponds to a horizontal expansion. Instead of x squared, we could have x divided by 10 squared. And these both are saying the same thing. And again, you should feel comfortable working in both systems.